All right, good morning. It's 11. Time to get started. A couple of announcements, reminders you'll see there, top of the page. First thing, remind you again, our last test is next Tuesday, 8 a.m. Again, it's not going to be from 8 to 11, just 8 to 9:30. And tomorrow is our last day of quote class. And we're not going over anything new tomorrow. All we're going to do is uh, review what's going to be on the test and answer any questions you have. So it basically, again, it covers everything that we've done since our previous test. So chapter 11, 8, and basically what we're going to do today would be the last thing you're responsible for on the test next Tuesday at 8 a.m. Other announcement I want to make right below that, if you noticed on in Canvas the list of suggested problems, I included on that a few problems from sections 12.6 and 7 in the book. I had kind of hoped that that would be the last thing we would be able to do, but time-wise, we're not going to be able to do that. If you're curious and wondering, basically what's in that section is solving statically indeterminate beams using the double integration method, the method that we've been doing the last couple of classes. And just remind you, if it's a statically indeterminate beam, basically what you would see in that section is you have beams that have more supports than are necessary. So consequently, you have more than 3 unknown support reactions, and you can't solve for all of those using statics. So that's why they're called statically indeterminate. And just FYI, it turns out we can solve those exactly the same way we did the statically determinate beams using double integration. It's really nothing at all different far as the procedure goes. So basically, there was nothing new to go over. I needed to work an example or two to illustrate that, and we're just not going to have time for me to work an example. And so, since I don't have time to work an example for you, I would not put a problem like that on the test. Therefore, don't worry about solving those. All right, so our last topic that you are responsible for is solving for beam deflections using method of superposition. And this is in section 12.5 in your book. And that's what we're going to talk about today. I think you'll find, like solving these, solve using this method better than the double integration method. So I reckon with that, let's get started. And basically the concept here, when we say superposition, basically what we've got is for beams with multiple loading, basically what we're going to do is just get the deflection due to each loading and then add those together. That's the concept of superposition. So we're going to compute deflection and slope if you want to. We can do both. It doesn't matter, deflection or slope, for each loading. And just add the results for each. So basically, we got a beam that's got more than one loading acting on the beam. we just break it up and get the deflection and slope if we want to for each individual loading. And to get the total deflection, you just add them together. Or if you want the total slope, add those together. So just a kind of illustrative example, kind of illustrate the concept here. Say we got a beam. Let's make it simply supported with a pen and ruler. And maybe we put a distributed load on half of this. And so we got some distributed load. We call it W naught. And maybe we got some concentrated force P. All right, so if we put that loading on this beam, it's going to cause it to bend. It's going to deform, and I don't know exactly what shape it would look like, but there would be some nice smooth curve. Again, it's greatly exaggerated, right? And that would be whatever the equation of that deformed beam is. That's our equation of the elastic curve, as he likes to say. So if we want to find that equation, basically what we do is just break it up into two individual loadings. Look at a beam with, say, just the distributed load on it. Right? And that's going to cause the beam to bend and deform, and we'd get some equation for that. We'll call it y1 of x. And then we look at the beam with just the concentrated force on it. That's going to cause the beam to deform and bend, and we get a different equation for the deformation due to that loading. Well, to get the equation for the combined loading, you just add those two together. That's the concept of superposition. Now, hopefully you're listening and thinking, well, you know, that conceptually this is pretty straightforward idea and concept. But some of you also, if you haven't looked ahead and looked in the book and know anything about this, you might be thinking, yeah, I get the concept, that's great, but I don't see how this is going to make life shorter and easier for me, because I still got to go through and solve for this loading, then I got to go through and I got to solve for this loading, which the second one, basically that's the problem we did yesterday. And so if I got to go through all that for each loading, then, you know, how is this going to be better? Well, thankfully, somebody has gone through and actually computed the results for these individual loadings. So I'll say many individual loadings have been solved. So somebody went through and did what we did yesterday and got the result for that. And the results are provided in a table. And in your textbook, you'll find this, I think it's Appendix C. So we take our beam with the multiple loadings, break it up into individual loadings, and then we go to a table, and from that table we can get the results for the deflection or slope for the individual loadings, and we just have to add them together. So we don't have to actually go through and calculate those individual loadings. In fact, I made a copy here. This is Appendix C out of your textbook. Looks like it's on page 814. If you got your book, if you want to pull out your book and look, and what you'll see, this is a table for simply supported beams. So These beams have a pin and a roller support. And you see, it looks like 6 different individual loadings. And for each of those loadings, you'll see in this column, typically what's given in these first 2 columns are maximums. So it tells you what the maximum slope or angle is. This formula tells you what the maximum deflection is and shows you where that occurred. For this being an isometric loading, the force right in the middle, maximum displacement's right in the middle, and that formula gives you the maximum displacement. So all you got to do is just plug in, again, P, L, E, and I, and you got your displacement. And this last column over here is typically where you'll find the actual curve. Now, note in the textbook, the notation here, I mentioned this the other day, but the textbook here uses V instead of Y. So just again, be aware of that. When you look at this, you'll see it's V max and V. That's what we've been calling Y. Now, I don't know why it's using V here instead of Y, but I'm going to use Y because I like using Y, because when I see V, I'm thinking shear force. But anyway, we've got this nice table. It's got the results for these 6 different cases. Now, there are much more extensive tables out there available that you can find a lot more than 6. But this gives you a good sampling. And we'll talk about in a minute. You can actually use this to, if you're creative and can actually do more than just 6 with using these that are provided. But we'll talk about that in a minute. But this is the first page in Appendix C. And then on the next page, I'll put it up here, you'll see this is a table for cantilever beams. So these are beams that have a fixed support at one end. And looks like there are 6 of these provided as well. And formulas to give you slope, deflection, and what the actual equation for the elastic curve is. All right, and so that's what we're going to use. We're going to take a beam, break it up into individual loadings, come back here to the table, find the appropriate formula, and just write down the right formula and plug in, if we got numbers, plug in our numbers, and we're done. Right, and this formula will be provided on your test Tuesday. Right, I certainly don't expect you to try to memorize the table with all these formulas on there. So this will be provided. All right, so let's look at one. There's some good examples in the book where you can look at those as well. But I'll start on a new page. Let's try this one. We're going to find deflection, and we'll do the slope as well. So we'll get the deflection and the slope at end B. So we've got a cantilever beam. It's fixed at this end. We'll call this end A. And we got 2 loadings on here. We have a distributed load that's linear. Draw a straight line. So it's goes from a maximum, we'll denote with W naught, and again decreases linearly down to 0 at the end of the beam. We'll call this B. And then we also have a concentrated force P out there at the end of the beam, and this beam has some length L. All right, so again, this is our beam. We've got these two loadings on there. And what this is going to do, it's going to cause this beam to bend, right? And it's going to deform. There's going to be a nice curved shape. And what we're asked is to find what is this displacement y at the end, b, and also, again, what would be the slope. And remember, since we're dealing with really small angles, basically slope and angle are used interchangeably. Because if you get a really small angle, it's equal to the slope. And so that's what we're asked to find. How far is the NB going to move down? And what's going to be the angle or the slope at that end? So how we do this, again, is we're going to break it up into two individual loadings. We'll do the distributed load first. So we've got this beam. It's got fixed support at A, and we put this distributed load on there. And then we got a fixed support again at A. So we got this cantilever beam with just a concentrated force out at the end of the beam. Now here's where we're going to go to our table and get the formulas for the deflection and the slope at this NB for those two individual loadings, and then we just add them together. All right, so here's where we go to Appendix C, and I'm going to bring my table back out here. And the one for the distributed loads all the way down here at the bottom. All right, so this is exactly what we have. All right, we've got a cantilever beam with a fixed support and a linear distributed load. And we've got a formula for the maximum displacement. Right? And again, the negative here is just indicating, positive is up. Right? So this is positive. So obviously, if you put that load acting down, it's going to move down. That's why you get the negative. And that would be minus W naught L to the fourth over 30 EI. Right? So I'll come back over here, and we'll call this YB1. And it's minus W naught L to the fourth over 30 EI. Right, and again, where that came from was this table. We also have a formula, right? Because the maximum displacement and the maximum angle, they occur at this free end. Right, that's where we get. This is our end B. So these are the two formulas we need. So write this formula down for theta B minus W naught L cubed over 24 EI. Right? Any questions where I got those two formulas off that table? All right, nobody's speaking up, so I'm assuming you're with me. All right, well now, this one actually good because it's at the top of the table. I can see both at the same time. So for this loading with the concentrated force at the end, again, the maximum displacement and the angle are going to occur at that end, right, that's what we're trying to find. And so I've got these two formulas, what I'm going to use to get my maximum displacement. So I'll call this YB2. It's just minus PL cubed over 3EI. And the angle or slope there at that end is minus PL squared over 2EI. Right? And again, somebody has gone through and used possibly the double integration method. I told you there's other methods also in chapter 12 that somebody could have used to, and actually went through and solved and got these results. That's where this came from, right? Somebody didn't just make it up, pull it out of the air. But it's important that you know how to do some other method like the double integration method, because, what happens if you run into a beam's got loadings not in the table? Well, if you don't know another way to do it, then you're in trouble. So that's why we have to do at least one other method in addition to using the table. Another thing I'll just mention, I mentioned a minute ago that you see these negative signs because the positive is up. Just to point out, if you had a beam like this where instead of the force P acting down like it is here, if you had a beam where you had, say, P was acting up, right? The only thing that's going to change is the sign, right? This thing is still going to have the same equation, elastic curve. You're going to get these same formulas, but obviously for this, it would deform up, right? It would bend up instead of bending down. So the only thing that would change here, right, you would get a plus, right? All these signs where these negative signs are would now be positive. So if you have a loading that's in the opposite direction of the table, you just change the sign. All right, everybody clear with me on that? It's like if our distributed load down here had been acting up instead of down, this would be positive. This would be positive. This would be positive. All right, so any questions how we got our formulas from the table? All right, we just all got to do now is just add them together. So if we want deflection, just add them together. So take YB1. Actually, this is just the deflection at B. So just add those together. We got minus W naught L to the fourth over 30 EI minus PL cubed over 3 EI. That's it. Whole lot shorter and easier than what we did yesterday. All right, but any question where that result came from? And I will just mention, you'll find when you look, if you're solving those suggested problems and you look at the answer in the back of the book, he likes to kind of go crazy and do a lot of factoring out a bunch of stuff. And I reckon that the intent is maybe to make it look better or more concise, but most of the time he's just doing more algebra for the sake of doing algebra. So it's fine with me. You could just leave it like this. You don't have to do a bunch of factoring and try to make it look pretty, like the answers in the back of the book. Don't worry about that on the test Tuesday. You can just stop right here. It's fine. And we get the slope at B by just, again, adding the two results together. Just add them together. We got minus W naught L cubed over 24 EI minus PL squared over 2 EI. So if we actually had numbers for the loadings and the dimensions and the material property and what the cross section's moment of inertia, again, you just plug the numbers in and you actually get the deflection and slope at that end. All right, so I'm assuming y'all like this better than what we did yesterday. Well, and the question is, can you just use the maximum for these problems? Well, for this problem, yes, because this problem asks for the deflection and slope at end B, which is where you get the maximum, right? This is y max, this is theta max. Now, I'll go back to the table. If it had just asked for, say, the equation of the elastic curve, right? If it had asked for that instead of the deflection at end B, right? Then we would have used this equation, right? This would give us the deflection, again, for any x, right? And then down there at the bottom, right, we would have used that. And we would have added those two equations together to get the equation of the elastic curve. But this problem didn't ask us to do that. It asked for the deflection slope at the end B, which is the free end where we get our maximum. That's why we used those formulas. All right, we're going to work an example in just a minute where we'll need to use the elastic curve equation. We can't always just use the maximum. Depends on what the problem asks for. All right. Now, one little observation before we look at another example. Now, I mentioned if you're creative, you can actually use that table for more than just the 6 cases that are shown there. For example, this one, looking at my table, this one's in the table, right, where we've got distributed load that's acting over half of the beam. We also have one where the distributed load goes the whole length of the beam. All right, so this is in the table. This is in the table. I'll put my table back up here and show you, right? We've got this one where it goes over the half of the beam. You got this one that goes over the whole beam. But what you see not in that table is one where you got a cantilever beam where you've got the distributed load. Right. This is not in the table. Right, go back and you look at this table. You don't see that one. Right? We don't have a fixed cantilever beam where we've got the distributed load, say, over just that half of the beam. But we can get creative, right, and basically kind of do what we did up here. This is equal to one where the distributed load does go the entire length of the beam. All right, remember that one? That's in the table. And then we subtract this other one that's in the table. All right, so again, this one's in the table, and this one's in the table. Well, this one is just the sum of those two, and so we can actually get the solution for this loading by taking this one and subtracting that one. And so it's something to keep in mind. If you see a loading, it's not exactly like one in the table. Think about, is there a way that you can take 2 of those that are in the table and either add or subtract them to get the loading that you want? And it's a nice little trick that you can actually use to, again, solve some problems other than just those 6 that are listed there. All right, that makes sense. Any question about that? All right, then let's do one more. Let's do a beam that's simply supported. Get the other table here in just a minute. All right, speak up, or can I change page? All right. So let's try this one. We'll actually put some numbers in this one too. I know most people like problems with numbers. So here we've got a W 200 by 22 beam. So this is a wide flange I-beam. And it's made of 2014 T6 aluminum. And I was nice, and I went and looked up what the modulus of elasticity for 2014 T6 aluminum. It's in that material property table that we talked about back earlier in the semester. And I looked that up, and I got E was 73.1 gigapascal. So in the real world, if you were solving this, you would have to go to that table, whatever material property table you got, and get what E is. Also went and looked, in that table with all the standard size beams, and I looked that moment of inertia up, and I was 20 times 10 to the negative 6. That's meters to the 4. So I looked those up, so we don't have to do that. And we want to find what the deflection at the center of the beam. That's at point C. So we've got a simply supported beam. Pin and roller. And just while I'm thinking about it, this is the way the beam looks in the table. You'll see in a minute. It's got a pin at the left end, a roller at the right end. But it really does not matter at all which one is which. So if you see a problem in the book where the roller's at the left end and the pin's at the right end, that does not change anything. It behaves exactly the same. And this is A, this is B, and C is right in the middle. And this is distributed load, constant, goes the entire length of the beam, and it is 1 kilonewton per meter. So mine kind of looks like it slopes down there, but it's because I can't draw a straight line. But it's constant. 1 kilonewton per meter over the entire length of the beam. And then here at point D, we've got a concentrated force applied. So in addition to the distributed load, we've got a concentrated force of 2 kilonewtons acting at point D. And this is 2.5 meters from A to C, and then 1.5, well, that's kind of hard to read, 1.5 meters and 1 meter. C's right in the middle. It's a 5-meter long beam. Point C is right in the middle, 2.5 meters on either side. And then we've got the distributed load, and then this concentrated force applying 1 meter from the right end. And we're asked to find what is the deflection at the center. So how far does point C move down? Right, this thing's gonna, it's gonna bend, and it's gonna bend down. So we want to know how far is the center of that beam gonna move down. So break it up into, again, the two cases. We've got the distributed load. Draw a straighter line this time. Yeah, it's 1 kilonewton per meter. And we want to know, again, how far is that going to make point C move down? And then we've got our second loading, which is just this concentrated force, 2 kilonewtons. You see, here's B. We've got 2.5 meters, 1.5 meters, and 1 meter. All right, so that's, again, that's my two loadings. And we're going to get how far C moves down due to this loading, how far it moves down due to that loading, add them together. Simple as that. All right, so we go to our table, Appendix C here, and see what we can find for, we'll call it YC1, and then we'll call this one 2. So we go to the table, and again, now we're looking at the simply supported, again, pin and roller at the end, and this is what we have, right? We've got a distributed load constant over the entire length of the beam, right? And due to symmetry here, right, our maximum displacement is going to be at the center. Again, this is due to symmetry. So this formula that we have here for Vmax, or I call it Ymax, right? This is the deflection, the displacement at the center. Okay, so that's the formula we're going to use to get the displacement or deflection of point C due to the distributed load. So let me write that in over here. Again, it's negative because positive is up. This thing's going to move down. Minus 5 WL to the 4th over 384 EI. Now again, that's all I've done is just copied this formula right here for the displacement of the center of that beam due to the distributed load. Okay, and then we put that in here. All right, so we know what the distributed load is. We know what the length of the beam is. We know E and we know I. So in a minute, when we add these together, we'll be able to plug numbers in here and actually calculate, how far this thing moves down. Now, for this one is a little bit different in that if you go to the table, what we have here is actually this case, right? Our force P is not in the center. Right? That force was applied, this is 4 meters. This is 1 meter. That force is not right in the middle. Now, if it was in the middle, right, we could use this one, and we know we're going to get the maximum deflection at the center, and we could use this formula. But the fact that our force P is not applied at the center, right, we got to use this case. Now, we don't, here's where, the question that got asked earlier, can we always use the formulas for the maximums? Well, here the answer is no. One, this doesn't give us a formula for the maximum displacement. It's not going to be at x equals a. We saw that from the problem we worked yesterday. This is basically the problem we worked yesterday. That maximum displacement is not where the force is applied. Now, they give us a formula for the displacement at A where the force is applied, but that's not what we were asked to find, right? We were not asked to find the deflection at point D, right? That's what this formula here would give me, the deflection where that force is applied. That's not what we were asked to find. We were asked to find what's the deflection of the center. Right, so we can't use this. This does not tell me what the deflection at the center is. So for this one, we've got to use this formula, right? This is the displacement or deflection as a function of x, right? So what we're going to have to do is use this equation, right, and plug in whatever x value that we're asked to find. In this case, we're asked to find deflection when x is like 2.5, right? That's what x is at the center. Also note, again, this is for x values between 0 and a. Right? Here's a and b are these dimensions. So this equation is only going to be valid for this part of the curve, from this end up to where the force is applied. But that's what we have, right? We have, when you look at this, our beam here, right? This is A and this is B in that formula. And C is located between 0 and A. So this formula is valid, right? C is at x equals 2.5. So what we got to do is take this formula and plug in x equals 2.5 to get the deflection at the center C. So I'm just going to write down the equation first. So what I've got here, I'll call it y2 of x. And I'll double check, make sure I write it down correctly. I got minus p bx over 6 EIL times L squared minus B squared minus X squared. Right? So I don't know if we can, it's going to cover it up, but I think I got it right. Minus PBX. I think that's right. All right, so that's where I got this formula here. All right, and so what we need to find, I'm going to move the table out of the way. All right, so YC2 is going to be when x is 2.5. So we need to plug 2.5 in here. So we'll get minus PB, not x, 2.5 over 6 EIL L squared minus B squared minus 2.5 squared. All right, so this one, again, a little bit not quite as straightforward as the one with the distributed load. But this is a good example where sometimes, if that table doesn't give you the deflection or slope of the specific point that you're asked to find, you're going to have to use that equation elastic curve and then plug in, whatever x value your point is at. Any question about that? All right, so now it's just a matter of, let's plug in the numbers. So to get the deflection at C, we just add Add those two together. Right, so we got minus 5 WL to the fourth over 384 EI. And then we got minus PB times 2.5 over 6 EIL times L squared minus B squared minus 2.5 squared. Right? And we know A is 4. We don't have an A in here. B is 1. Right? So I know B is 1. L is 5. And then I think that's all we got. Well, P is 2 kilonewtons and W is 1 kilonewton per meter. So let's just plug in the numbers. So we get minus 5. And when I'm doing SI units, I like to do everything in newtons and meters. So instead of, again, for W, instead of 1 kilonewton per meter, I'm going to go ahead and write it as 1,000 newtons per meter. The length is 5. Right, so we get 5 to the fourth over 384 times E, 73.1 gigapascals. That's 10 to the 9th pascals. And then I is 20 times 10 to the negative 6 meters to the fourth. And likewise for P, it's 2 kilonewtons, but I'm going to go ahead and put in newtons, 2,000 newtons. B is 1 meter, 2.5. 6 times E is 73.1, 10 to the 9th. I is 20 times 10 to the negative 6. L is 5. And we're going to multiply that times 5 squared minus 1 squared minus 2.5 squared. Looks like a 6. That's a B. And then you pull out your calculator and crunch the numbers. And obviously, we're going to get a negative. This thing's moving down. And I got 0.00759 something. Let's just go 0.76 meters. And notice this is really small, right? And that's what we expect. And that's what we've said all along. The deflections are going to be small. That's what, 7.6 millimeters? I mean, you're talking about a 5 meter long beam, and right out in the middle, it's going to go down about 7.5 millimeters. So that confirms, our small displacement, small deflection assumption. Now, if we had got, say, 7.6 meters, then a couple things. One, I know most likely we did something wrong, right? Probably we're off by like, if you're off, if you say giga is 10 to the 6 instead of the 9th, you're just made this thing 1,000 times bigger. And so you would get 7.6 meters. But that should stand out as a red flag. Where do we get the I from? I looked it up in the table. I looked up in appendix, I think it's appendix B, where we had the beam, the standard beams. I looked up the W 200 by 22 I beam, and I got that out of the table. That's where I came from. But if you get something like 7.6, well, think about it. The whole beam's only 5 meters long. There's no way the center's going to move down 7.6 meters. It's going to break way before then. Again, so most likely what you messed up with your units or somewhere. And certainly, if you get something like that and you can't figure out where you went wrong, write me a note and say, I know this is way too big, but I just can't figure out what I did wrong. Because occasionally I'll see students, they'll solve a problem like this and they'll tell me the deflection like 760 meters. And I gotta assume you think that's right, and that tells me when you really don't have a clue as to what's going on. If you think that beam can move down 760 meters, uh, so if you get something is completely impossible, if you can't figure out what's going wrong, at least tell me that. Hey, I know this is not right. I just can't find my mistake. All right. Any question about that one? Any question, just anything related to this method we call superposition, and using those tables that's out of the back of the book in Appendix C, which again will be provided to you. All right, well then that's, again, the last thing you're responsible for on the test. So we're out of time, right on time. So that's where we stop. But as always, if you got questions about something else, hang on for a minute or two. Let me get the recording stopped, and I'll be glad to answer any questions you have.